So in the last class, we were discussing different moments. That means moments about the origin and central moments. Nth order central moment, nth order moment about the origin. Now we'll discuss in this class, we'll start discussing what is standard deviation, how to define standard deviation and variance. So the second central moment, I guess you can see the material. Is it legible or should I make it full screen?
It is legible.
So the second central moment, mu2, is very important and it's named as variance. So what is the formula? So if we want to find out the second central moment, so as per definition, sigma x square, this notation is used to denote the variance. So sigma x square is equal to mu2, the second central moment, and as per definition this is equal to expectation of x minus x bar, that means the mean value, whole to the power square. So that is the definition of second central moment. So we can write it as minus integration minus infinity to infinity x minus x bar, that is the mean value, whole square fx dx. Now the positive square root of this variance, that means sigma x, is known as the standard deviation of x. So from this formula, from this definition or from this definition, we see that the variance sigma x square is equal to the expected value of x minus x bar whole square. So that is equal to expectation of x square plus, sorry, x square minus 2 into x bar plus x bar square. So sum of expectation, so that will be expectation of sum of functions. These are the functions. So we'll get expectation of the sums. So this can be written as expectation of x square minus expectation of 2x into x bar plus expectation of x bar square. Now remember that x bar, that is the expected value or mean value, that is constant. So this will be expectation of x square minus, if we take out this constant value out of this expectation, then we'll get, and 2 as well. So 2x bar into expectation of x. So that will result in the expected value, again the expected value. So we'll get 2x bar square. Is it clear? The second term will be minus, because of the sign, minus 2x bar square. So this is equal to 2 into x bar is constant, and expectation of x, which is again x bar. And this is constant, so the expected value of this constant x bar square will be simply x bar square. And this is expectation of x square, that means this is nothing but the second moment about the origin, right? So from this 2 we'll get x bar square plus x bar square, sorry, minus x bar square. So this is equal to expectation of x square minus x bar square. So this is the second moment about the origin, so we can write it as m2, and this one we know that this is x bar is the first moment about the origin, so x bar square will be m1 square. So the variance sigma x square is equal to, or the second central moment can be expressed as the second moment about the origin minus the square of the first moment about origin. Now next is skew and skewness. We'll not discuss in detail, just we'll go through the definition. The third central moment, that means mu3, will be, as per definition, will be equal to expectation of x minus x bar whole cube. So this is a measure of the asymmetry of effects about the mean value or about the expected value, which is n1. So note that this third moment is generally known as the skew of the density function. It gives us the asymmetrical nature, it portrays the asymmetrical nature of the density function. And if a density function is symmetric about the mean, then it has got no skew. Since it's symmetric, so the skewness property of the density function will be 0. Now, what is the exact definition of skewness? The normalized third central moment, that means mu3 by 3 sigma x cube. Remember, this is cube, right? So this is the normalized third central moment. This is known as skewness of the density function, or alternatively the coefficient of skewness. Now, what is the significance of variance? I guess you know that. Let us consider two distributions. Actually, these two are the two normal distributions or two zero-min Gaussian distributions, and the random variables have been specified over here. The first one, you see, this n stand for normal distribution. So n and the parameters, arguments are, or you can say parameters as well. Arguments are mean value, expected value, and the variance. So here, this 0 signifies that it's a zero mean distribution, and in the first case, for the first case, the variance is 1. Whereas in the second case, again the mean value is 0, but the variance is 3. So if we plot these two density functions, this is the first one, this is the second one, we find that though the mean value is 0, and though the distributions, both the distributions are absolutely symmetrical about the mean value, which is 0 in this particular case, but the second one has a wider spread around its mean, which is 0, has a wider spread, and this is quite a narrow distribution. So with the help of one single parameter, exactly we cannot what should I say? We cannot actually describe the density function, right? So zero mean, yes, the mean value is important. Okay, so we'll have to find out whether the density function is symmetric about its mean value or not. But at the same time, to exactly describe the nature of the bell-shaped curve, how wide it is, whether it's a steeper one or not, we require the second parameter, which is the variance in this particular case. So the following additional observations can now be made. Case 1, the random variable x1 is more concentrated. This one. So more concentrated about the mean. However, x2 has a wider spread. It's quite apparent from these two plots. Now the conclusion is clearly we need at least one additional parameter. Apart from the mean value, we need at least one additional parameter to measure the spread around mean. Now, for a random variable which is of discrete type, it's obvious that sigma x squared, the expression of the standard deviation or the variance, rather this one is the variance, will be given by summation of I going from 1 to n pi xi minus mu whole square. That we can derive from the definition of the variance given for a continuous random variable. Only this fx part is replaced by the corresponding probability. Clear?
Yes, ma'am.
Now we'll discuss two inequalities, and after we finish discussing the distribution functions or density functions, various density functions, then if time permits, we'll come back to these inequalities and we'll try to understand what is the, with the help of example, we'll try to understand the exact meaning or concept of these inequalities. Now the first one is Chebyshev's inequality. So what is the statement? Let us consider a random variable with probability function fxx. This is given, this is the density function, and let x bar is equal to mu be the mean value and sigma x be the standard deviation of x. Then Chebyshev's inequality states that probability that mod x minus x bar, that means the deviation of the random variable from its mean value, in either side. So mod x minus x bar greater than a, that means the deviation on either side should be greater than equal to a, will always be, and the probability of this will always be less than equal to sigma x square by a square, this a square for any a which is greater than 0, right? So this is basically the Chebyshev inequality. So this deviation should not be greater than equal to a, and the probability of that is always less than this value. So we'll have to prove that. So this means that if we select any number a, then the probability that x will differ or deviate from its mean value, x bar is equal to mu by more than a, is less than sigma x square by a square. So x is unlikely to differ from mu by more than a few standard deviations, and therefore the standard deviation sigma x gives an estimate of the spread of the distribution. Okay. For example, if a, this value a is equal to twice sigma x, then for the time being, if we assume that yes, this is true, this condition holds, then if we put the value over here, we'll get the probability to be equal to 1 by 4. Quite less. So proof of Chebyshev's inequality, this is suppose this is not a zero mean, we assume that this is the mean value. So this is a bell-shaped Gaussian distribution, and this is the mean value, and we have identified the region where the random variable is actually deviating from the mean value. This mean value mu is nothing but equal to x bar. Okay, so we have shaded the region which falls under these 2 points, that is x bar minus a or mu minus a and mu plus a. We are trying to find out a is any value and greater than 0. We are trying to find out that what is the probability that the distribution or the random variable will lie within the range or will exceed this particular range. That is the essence of Chebyshev's inequality. So you say probability that x minus x bar greater than equal to a can be written as, this is the mod, can be written as, that means this is the, we are trying to find out that the probability that this deviation is greater than equal to a will be equal to, you see, minus infinity to x bar minus a, that means this area, fx dx plus this area. So the area will be denoted by integration x bar plus a to infinity fx dx. Is it clear?
Yes.
So in this region, you see the deviation is less than this value, right? And here we are trying to find out whether the deviation is greater than equal to a. Hence, we are trying to find out these two areas. We are evaluating these two areas. So these two together in a combined form can be written as integration mod x minus x bar greater than equal to a fx dx. Now, we know that by definition sigma x square is equal to integration x minus x bar, minus infinity to plus infinity, x minus x bar whole square fx dx. Just we have seen this definition, right?
Yes, ma'am.
So this area will always be greater than or at best equal to the area given by this x minus x bar square fx dx, where the limit is varying within this. Here the limits are from minus infinity to plus infinity. Here the limits are less than minus infinity and sorry, greater than minus infinity and less than plus infinity. Hence, this area will always be less than this area. Sorry, this area will always be greater than this area.
Yes, ma'am.
So now we assume that this deviation, that means this one should always be greater than a square integration minus x. The limits are x minus x bar greater than equal to a fx dx. Because now this becomes a square, right?
Yes, ma'am.
So this is greater than, this area is greater than a square fx dx, where the limits are given by this, and that is equal to, this is nothing but a square into probability that x minus x bar is greater than equal to a. We have started from this. So this one, this expression multiplied by a square, right? So that is nothing but a square into probability x minus x bar mod of that greater than equal to a.
Yes, ma'am.
So the probability that mod x minus x bar, that means this deviation will be greater than equal to a, is certainly less than equal to, sigma x square by a square. This probability will be less than sigma x square by a square.
Yes.
So less than or equal to. So we can write that probability, this is the same expression actually, only we have replaced this x bar with this notation mu. So this excursion will be greater than a. The probability that this excursion, this deviation around the mean will be greater than equal to a will be less than equal to sigma x square by a square. Hence, we see we have proved the Chebyshev's inequality, and we have seen that Chebyshev's inequality holds. So let's consider one example. So we find the largest probability that any random variable's values are smaller than its mean by 3 standard deviations or larger than its mean by the same argument, right? So this question, this problem can be posed like this. So probability x greater than equal to x bar plus 3x. Any random variable's values are smaller than its mean by 3 standard deviation or larger than its mean by the same argument. So x greater than equal to x bar plus 3x plus this probability, that is probability x less than equal to x bar minus 3x. Is it clear? So we are trying to find out this probability. Have you understood this?
Yes, ma'am.
So this is nothing but the probability that mod x minus x bar is greater than equal to 3x. So now directly we can apply Chebyshev's conditions. So here, this is the value a, right? So this probability will be always less than sigma x square by a square. Now what is the value of a? The value of a is 3x, so it will be a square, so 3x square, or that is equal to 1 by 9 or only about 11%. Now, an alternative form of Chebyshev's inequality can be proved. So it states that that was greater than equal to, right? Right? Now here we are using the sign that is less than. That is, this deviation will be less than a value which is given by epsilon. So directly from this we can derive this probability that will be given by greater than, so this probability will be greater than equal to 1 minus sigma x square by epsilon square for any epsilon which is greater than 0. Please do check whether you have understood this or not. Have you understood this formulation?
Ma'am, can you explain the alternative form again?
This one, have you understood the basic Chebyshev's inequality?
Yes, ma'am.
So here we have used a sign that is greater than equal to ax. Now the other event could be x minus x bar. That means mutually exclusive event could be probability that event could be x minus x bar mod, which is less than a.
Yes, ma'am.
It is greater than equal to a. So the other event could be less than a. We are trying to find out that particular probability, right? And we know that the total probability, that means the probability of this event plus the probability that p x minus x bar less than a, right, will be equal to 1. Yes or no?
Yes, ma'am.
So that's why now this sign will change. So probability x minus x bar less than epsilon will be greater than or equal to 1 minus sigma x square by epsilon square, since the total probability or area under the curve for a PDF equals 1.
Okay, ma'am. Understood.
Yeah. So an interesting observation you see, I don't know, from this if should not be here. Now look at this expression. So if we assume that the standard deviation, or in other words, the variance is tending towards 0, that means there is almost no spread around the mean for the given density function, right? And that's why the variance is tending towards 0. Then this probability will tend towards 1, since sigma x is tending towards 0. Hence this probability, that means x minus x bar less than epsilon, will tend towards 1 for any value of epsilon. Oh, if is it clear?
Yes, ma'am.
It's very simple. This probability will tend towards 1 since sigma x is tending towards 0. So with the help of logic, we can corroborate this, or we can justify this result. You see, when sigma x is tending towards 0, it means that there is no distribution or spread around the mean. So the random variable will be totally concentrated on its mean. There will be no spread, no deviation from the mean. That's why the standard deviation is tending towards 0. So it follows that if sigma is equal to 0, the probability that the random variable x is outside the interval mu plus epsilon and mu minus epsilon. For any epsilon could be very, very small, but in that case also, that the random variable, the excursion of the random variable will be beyond these two values. Mu plus epsilon and mu minus epsilon will be 0. Hence, x equal to mu, this will have a probability which is equal to 1. Is the logic clear?
Yes.
Now, second inequality, the Chebyshev's inequality is a stricter inequality compared to the second inequality that we are going to discuss, that is Markov's inequality. Why? That we'll discuss after completing third chapter. So Markov's inequality applies to a non-negative random variable x. That is the condition, non-negative random variable x, and is given as if fx is 0 for x less than 0. That means for negative values of x, the distribution function is 0. So under that particular condition, for any alpha greater than 0, probability that x will be greater than equal to alpha will always be less than the expected value of the random variable divided by alpha. So proof of Markov's inequality, expectation of x as per definition is given by integration 0 to infinity. Why it's not from minus infinity to infinity? Because of this particular reason that we have already seen. Fx is 0 when the value of the random variable is negative. So the limits of the integrations are varying from 0 to infinity. So the definition of the mean value will be given by x fx dx, right? So this area, why? Because we are integrating from 0 to infinity, will always be greater than or equal to, depending on the value of alpha, is equal to alpha to infinity x fx dx. Right? It's quite obvious, because instead of 0, now we are trying to evaluate the area under the curve from a value which is alpha, that is greater than 0. So this area will be greater than this area. And you see here, x can assume any values from alpha to infinity. But if we fix this, then the resulting area, suppose instead of x, if we write some constant value alpha, then the resulting area will certainly will be less than this value. So this area is greater than equal to alpha into integration alpha to infinity fx dx. Do you agree?
Yes, ma'am.
And hence from this we get that the probability that x is greater than equal to alpha is equal to this area. So we have got this. So the probability that x is greater than equal to alpha is given by ex by alpha. So less than equal to ex by alpha. So this probability will always be less than equal to ex by alpha. Clear?
Yes, ma'am.
Now we'll discuss. We have already discussed what is meant by moments. Um, Now we'll discuss how to generate these moments, nth order moments. So if we can find out, if we can compute the nth order moment, then putting different values of n like 1, 2, 3, we can find out the first moment, second moment, third moment, so on and so forth, right? So to compute the values of the moments, we use two functions which are named as the characteristic function and moment generating function. Characteristic function is also a moment generating function, but we'll see what is the difference between these two, right? So characteristic function can be used for generating moments as well as moment generating function can be used for generating moments. And a special case, in case of a discrete random variable, we use a function which we call probability generating function. Why we call it probability generating function, that we'll see. So we are going to discuss these three functions: characteristic function, moment generating function, and probability generating function. So the first one is the characteristic function. The characteristic function of a random variable x is defined as phi x omega. The argument is omega, and that is given by this integration minus infinity to infinity fx dx e to the power j omega x dx, right? So we can write this is nothing but this integration is equal to the expected value of e to the power j omega x. Can you recall this? Can you recall this, or do I have to show the expression once again.
Yes, ma'am. You can recall.
Okay, fine. So this is the expected value of e to the power j omega x. This is known to us. Now look at this function. Are you familiar with this expression? Can you identify this expression?
Ma'am, the inverse Fourier transform.
It's not inverse Fourier transform. It's basically the Fourier transform where the sine of omega is inversed. Isn't it?
Yes.
Yes,
So
ma'am.
now if we want to find out fx from this expression, then we'll go for inverse Fourier transform. So in equation, we see that fx omega is seen to be the Fourier transform with the sine of omega reversed. Fourier transform of which function? Fourier transform of fx, x, right? Only the sine of omega is reversed. So this is the characteristic function. This is called the characteristic function, which can be used for generating moments. So phi x omega is equal to integration minus infinity to plus infinity fx e to the power j omega x dx. And if you want to find out fx from this expression, then you know that fx will be given by 1 by 2 pi integration minus infinity to infinity phi x omega e to the power minus j omega x d omega. Okay. Now generation of moments. So we start with the characteristic function. Now we differentiate this function in times with respect to omega. Do you have pen and paper with you?
Yes, ma'am.
Okay. So if we differentiate this, then the left hand side will be dn phi x omega d omega n, right? And in the right hand side, out of the integration sign, we'll get j to the power n terms, right? And within the integration sign, we'll get minus infinity to infinity. This x will come over here, x to the power n, fx e to the power j omega x dx. Is this expression correct?
Yes, ma'am.
So this part is written over here, which is integration minus infinity to infinity x to the power n fx e to the power j omega x dx will be equal to minus j to the power n dn phi x omega d omega n. So what is this? We know that this will be the expectation of a function of the random variable. And what is the function? In this case, the function is x to the power n e to the power j omega x. So this expression is nothing but the expected value of this function defined by x to the power n multiplied by e to the power j omega x. And that is equal to, from this we see, minus j to the power n d n phi omega by d omega n. Clear?
Yes, ma'am.
So if we now try to evaluate the expected value for omega is equal to 0, so if omega is equal to 0, the left hand side will reduce to expectation of x to the power n
Yes, ma'am.
So that is our required nth order moment about the origin.
Yes, ma'am.
As per definition. So that is equal to minus j to the power n dn phi x omega d omega n. But this time we'll have to evaluate this derivative when the value of omega is equal to 0. Right? So that's why this characteristic function is called a moment generating function. So again, this can be written as integration minus infinity to infinity x to the power n fx dx, yes, omega is equal to 0, is equal to minus 1 to the power n d to the power dn phi x omega d omega n. Right? So by definition, the nth order moment about the origin is this one that we know, the expected value of x to the power n, just we have seen. So with the help of the characteristic function, we can find out the nth order moment about the origin, which is denoted by mn, and mn will be equal to minus j to the power n dn phi x omega by d omega n when omega is equal to 0. And hence phi x omega, which is the characteristic function, can be used for generating different moments. Now, in place of j omega in the characteristic equation, we have seen that was the characteristic equation. So, in the place of j omega, now let's substitute a variable which is s. So, replacing j omega by s, we get a function which we call moment generating function, that is phi x s. Now the argument will be s instead of omega, it will be s, and that will be given by integration minus infinity to infinity fx x e to the power sx dx, right? So this is nothing but the Laplace transform. Again, here we see that the sign has been reversed. Sign on n is sign on x is reversed, right? So we'll follow the same procedure. So differentiating this function n times with respect to s, we'll get dn phi x s by dsn, and that is denoted by phi to the power n xs, as it will give us the nth moment, and that is equal to infinity x to the power n e to the power sx fx dx, right? So again, this can be written as the expected value of this function x to the power n e to the power sx. So expected value of x to the power n e to the power sx, if we evaluate this expected value when the value of the variable s is equal to 0, then we'll get expected value of x to the power n. This term will become 1, and that is equal to dn phi x s by dsn when s is equal to 0. So this is our moment generating function, or phi is equal to phi x n s at s equal to 0. So if we replace the argument s by 0, then phi x n 0 will give us the expected value of x to the power n when s equal to 0, and that is nothing but our nth order moment about the origin, right? So from the first derivative evaluated at s equal to 0, we'll get the first moment about origin, which is the expected value of the random variable, that is x bar, is equal to m1, and you can see the derivation. I guess it's clear. Now the second moment about the origin, that is m2, To compute m2, we'll have to take the double derivative of this expression. So phi x double dash, that means d2 phi s by ds2 at is equal to 2 is equal to expected value of x square, which is the second moment about the origin. This is the first moment. Already we have seen. So the variance can be computed from these two values. So variance will be this one, double derivative of the moment generating function at is equal to 0 minus the square. That means the first derivative of the moment generating function at is equal to 0 square, the squared value of the first derivative of the moment generating function. Just see whether you have understood this or not.
Understood.
And this is obvious. Sigma x square is equal to m2 minus m1 square. That means m2, the second moment above the origin, can also be written as sigma x square plus m1 square. So this is your assignment. Do it right now. So let's consider a random variable with exponential density function. The density function is given over here. Fx is equal to 1 by b to the power x minus a by b, where x is greater than a, and 0 when x will be less than a. That means we are getting the density function for a value of x which is greater than a, right? So here we have described the exponential distribution function with the help of two parameters. One is beta, the other one is one is b, the other one is a, right? But the generic expression of an exponential density function is like this: fxx is equal to lambda e to the power lambda minus lambda x, sorry, e to the power minus lambda x. So generally we describe the exponential density function with the help of one single argument, which is lambda. So in this particular case, we find that, so if we want to if we want to map this density function into this, we find that the value of a will be equal to 0 and the value of lambda will be equal to 1 by b. First of all, find out the distribution function. The fx is given, density function is given, so find out the distribution function. From the density function, how could you be able to find out the distribution function?
And by integrating it.
Yes, do it. Do it fast. Have you evaluated the distribution function? Have you evaluated the distribution function? Yes or no?
E to the power a by b by e to the power a minus 1 by e to the power a.
Is
Yes,
it
ma'am.
same as this one?
Yes, ma'am. Same as this, ma'am.
All of you have done this. So this is the nature of the density function, and this is the nature of the distribution function. So now form the characteristic function. So you know the density function, from that form the characteristic function. And find out the mean and the variance. For the timing, just compute the mean, that is the first moment, about the origin. And computation of variance will be your home assignment.
We'll just do the Fourier transform of the density function, right?
Fourier transform of the density function with sine inverse.
Oh, yes. Sine inverse.
Just now we have seen that the characteristic function is equal to integration minus infinity to infinity fx into e to the power j omega x dx. That is the characteristic function. So take the first derivative of the characteristic function and evaluate it at omega is equal to 0. Just look at this density function, and hence it's obvious that for this density function, the limits of integration will vary from a to plus infinity. Have you computed the first moment about the origin? This is our characteristic function. What is the value of the first moment? Are you still taking the first derivative? Please respond. Hello, please respond. Are you there? Have you got this result? Yes or no? Please respond.
Yes, ma'am. Yes.
Have you got this result? Yes or
I'm
no?
calculating. Yes, ma'am. Yes, ma'am. Got this.
Got this?
Yes, ma'am.
So that means with the help of this example, we have already computed the mean expected value of the exponential distribution, which is a continuous distribution, right? A distribution of a continuous random variable. So this is the expected value. And if we express the exponential distribution in this particular form, so we know that a will be 0 and alpha sorry, lambda will 1 by b is equal to, or rather b is equal to 1 by lambda. Hence, the typical expected value of the exponential distribution is 1 by lambda, right? Now we'll have to find out the variance of this distribution. The density function is given. So take the second derivative of the characteristic function and proceed as we have seen the steps, and therefrom calculate the standard deviation. That is your home assignment. Now the third one is known as probability generating function, and this is basically a moment generating function for discrete random variable, right? So if the random variable is a discrete one, then we can write one function phi x omega. This characteristic function phi x omega can be written as summation of probability that x is equal to xi e to the power j omega xi. Since x is now a discrete random variable, so this is equal to, if I use a short notation for this, so this can be written as probability I, that is probability x is equal to xi, that is pi. So this characteristic function, instead of integration, now we'll get a summation sign. So summation over I pi e to the power j omega xi. Is that okay? So now we see, look at this expression. So phi x omega will now become a sum of exponentials and has the characteristics of discrete Fourier transform of the sequence pi, right? Now, if x takes only integer values, if you restrict the possible values of this discrete random variable to integer values only, then we define the z transform. This function can be defined to be a z transform. Again, the sign is reversed. So for a discrete random variable, the moment generating function is often called the probability generating function, PGF. So given a non-negative integer valued discrete random variable x with probability x is equal to k, which is equal to pk, the probability generating function PGF, in short, is defined as tau z. The argument is z, and it's the probability generating function of this random variable, discrete random variable x. So tau z will be equal to summation I is equal to 0 to infinity pi z to the power I. It will be replaced by z to the power I. This one, this part will be replaced. Do you have any question? Hello?
Can you repeat this part, ma'am? The discrete random variable.
I'm not discussing discrete random variable. I'm discussing probability generating function or moment generating function for discrete random variables,
Yes,
right?
ma'am, that part.
So let's start. Okay, let's start from this characteristic function. We are familiar with the characteristic function by this time, right? So in the characteristic function, you see the characteristic function was this. Just write it down. Please note it down. It will be helpful for you. The characteristic function was defined as phi x omega. Omega is the argument. That was equal to integration minus infinity to infinity fx e to the power j omega x dx. Note it
Yes,
down.
e to the power j
Now,
omega x.
okay, so note this down, this expression. Now, if we consider a random variable to be a discrete one, then the first thing that we'll have to do, we'll have to replace this integration sign with a summation sign.
Yes.
This fxx part, this will give us the probability that the random variable x will assume a value xi, a discrete value xi, that we know.
Yes, ma'am. Yes.
And this is the function. This is the function
Yes.
which is remaining. So now the characteristic function can be written as summation of all these probabilities, that probability x is equal to xi, where I is varying, and this part will remain e to the power j omega. Now, instead of x, it will become
The
xi.
xi.
Yes, as we are taking summation over I.
Yes, ma'am.
Now, look, this function again can be, if we replace this j omega xi by this part by zi, then please note down this function you have understood, right? How we are
Yes, ma'am.
getting.
Yes, ma'am. P at x equal to xi is pi and e to the power j omega xi. That
That was
integration
there.
is
Huh? Integration is replaced by the summation because we are discussing discrete random variable. So now this function, if you just replace this part, e to the power j omega by z, right? Then that the previous expression can be written as summation of probability x is equal to xi, right? X is equal to xi multiplied by z to the power I.
Yes, ma'am. Now, are we doing z or just z transform?
No. I'm not talking about z transform. We can first of all that particular discrete characteristic function can be written in this form.
Yes, ma'am.
Yes.
Is that okay? So this is our probability generating function, because in the previous case also where we use that j omega part, this j omega xi part, we saw that the summation is the summation of exponentials, sum of exponentials. Have you studied discrete Fourier transform?
Yes, ma'am. We have studied discrete Fourier transform.
So this expression looks like a discrete Fourier transform, isn't it?
Yes,
ma'am.
Just forget about the sign. Forget about the sign.
Yes, ma'am. Yes, ma'am. It looks like.
Right. And look-wise, you see, if I substitute this with the help of this variable z, then that particular expression can also be written as summation I varying from 0 to infinity probability that x is equal to xi into z to the power I.
Yes, ma'am. But
Right?
why are we doing z to the power I instead of z suffix I?
No, why it should be a suffix? It's to the power.
Ma'am, we replace e to the power j omega xi as z, right?
E to the power?
J omega xi as z.
No. Come, look at this. We know that if the uh, discrete random variable is non-negative integer valued function, then we know that probability x is equal to k is given by pk, right? So now we can write it as, suppose this is the function we define tau z, that which is given by summation of I varying from 0 to infinity pi z to the power I,
Okay, ma'am.
right? So if we expand this, then we'll get p0 plus p1 z plus p2 z squared. That means p0 means probability that the random variable is assuming a value which is 0. So this summation uh, can be expressed as summation of px is equal to I z to the power I,
Yes, ma'am.
right? So now this expression is having a look like a z transform if only this condition holds.
Okay, ma'am.
Right? So let's see now whether we can work with this or not. We can work with the previous one as well, but it will be easier to use this particular form. So you see, if we evaluate the function for a value of z which is equal to 1, then this summation will be equal to 1. This will be summation
Yes,
of
ma'am.
pi, isn't it?
Yes, ma'am.
Summation of pi 1 to the power I, or if I look at this, so we'll get p0 plus p1 plus p2 plus pk, so on and so forth, right? So tau x1 will have a value which is equal to 1. Sum of all these probabilities, p0, p1, p2, etc.
So we can determine the variance from it.
No, not now. Let's see. Only we have computed the value of this function when the value of z is equal to 1, right? So by definition, tau z is equal to summation over k, probability x is equal to k, as the random variable is a discrete one, multiplied by z to the power k. Is it okay?
Yes, ma'am. This is okay.
So now this can be generalized. This can be generalized as the expected value of this function, where now we are changing k to a variable x. This is basically the part which is fx dx, right? That is the probability part. And this is the function z to the power k. So in general, we can write this as expected value of z to the power x. Clear?
Yes, ma'am.
So now again, we'll start differentiating. So if we take the first derivative of this function, we'll get
Expected
tau.
value of x into x minus 1 z to the power x minus 2.
Yes, this no, z to the power x minus 1.
Oh,
X into
first,
the first
I thought
derivative.
this is second. I did the second derivative. Okay.
First derivative is
X into z
expected
to the
value
power
of,
x.
right. Again, if we differentiate that, that means we are taking the second derivative of this one, we'll get tau double dashed z is equal to expected value of x into x minus 1 z to the power x minus 2. So if we go on taking derivatives in this manner, and if we differentiate that expression k times, we'll get tau xz. We have differentiated k number of times, so that will be equal to the expected value of x into x minus 1 into x minus 2 into x minus k plus 1, and whole will be multiplied by z to the power x minus k. Just extrapolate from this expression or this expression.
Okay, ma'am.
So previously we were evaluating the functions where the argument, the value of the argument was considered to be 0. Now, in this case, let's assume that the value of this argument z is equal to 1. So if z is equal to 1, then the right hand side will be nothing but the expectation of x into x minus 1, x minus 2, x minus k plus 1 into 1. Since z is equal to 1, so this part will become 1. Here.
Yes.
So, look at this first derivative. So, in the first derivative, already we have seen that tau x1 is equal to 1. That we have already seen. That is tau x1 is equal to p0 plus p1 plus p2 dot 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 dot. Now, that is the first derivative. So, if we evaluate the first derivative at z equal to 1, then this part will be 1. So, we'll be getting the expected value of x, which is nothing but the expected value of x, or the first moment about the origin.
Yes, ma'am.
Now, the second derivative, let's look at the second derivative. So, here again, if we evaluate that at z is equal to 1, then we'll get the second derivative will be equal to, at 1, will be equal to expected value of x into x minus 1. That is, it will be equal to expected value of x square minus expected value of x. Is it okay?
Yes, ma'am.
So this expected value of x square can be computed from this expression. That means tau double dash 1 plus expected value of x. That will give us the second moment about the origin, isn't it? This one was the first moment, but the second moment about the origin is equal to tau double dashed 1 plus ex. Clear?
Yes, ma'am.
So what is sigma x square? If we now try to find out the standard deviation, we know that the standard deviation is given by expectation of x square minus mu square or m1 square. That means the square value of the
Expectation
expected
of x.
value. Right. So here we'll substitute this value to find out the standard variance. So e x square, expected value of x square, will be tau double dashed 1 plus expected value of x, and this third term will be this one, that is minus expected value of x square. So this
Which is
expression,
tau single dash x square.
it is also
ম্যাম বলছি ম্যাম ex টা তো তো হচ্ছে টাও টাও সিঙ্গেল ড্যাশ এক্স ওয়ান
good. This one, yes, yes. This one.
সেটা আবার সাবস্টিটিউট করব কি করব না?
করতে পারো নাও করতে পারো। We are assuming that we have evaluated this one, because you see, if you want to find out the standard deviation, sorry, the variance, then it's clear that you'll have to find out the second moment about the origin, right? And the standard deviation is the second moment m2 minus the squared value of the first moment. Okay, so that means you'll have to evaluate m1 as well as m2. So you can substitute this value over here, no problem. But I'm assuming that already you have computed tau dashed 1. That means you have computed the first moment, right? So for second moment about the origin, we have taken the double derivative as usual, right? And now we see that this is the second moment about the origin. So to compute the variance, now we can use this formula, or you can write it as tau double dashed plus tau dashed minus expectation x square. That you can write, no problem. Is it clear? What I'm saying, is that clear?
Yes, ma'am, understood. We have to memorize this equation, this expression, or we have to derive everything.
You'll have to derive that. So now let's take one example, discrete case. Here we are considering Bernoulli's trial. Okay, so the first example is this one. X takes the values of 0 and 1. Have you studied Bernoulli's trial?
Yes, ma'am. Like we know what is Bernoulli's trial.
Fine. So we can have two values, 0 and 1, say coin tossing, with probability x is equal to 1 is equal to p, that the probability that this random variable will assume this discrete value 1 is p, and the probability that the random variable will assume this discrete value, which is equal to 0, is given by q, right? So then we know that from the theorem of total probability, p plus q will be equal to 1, isn't it?
Yes, ma'am.
So now let's form the probability generating function, that is tau z. Here I have dropped the suffix, which is x, so for notational convenience. So tau z is equal to probability x is equal to 1 into z to the power 1 plus probability x is equal to 0, z to the power 0. I'm coming back to that. This is the form. This is the form. So now the summation, within the summation, will get only two terms. One for probability that is x is equal to 1, and other one for probability that x is equal to 0. So the probability generating function tau z will have a form which is equal to probability x equal to 1 z to the power 1 plus probability x equal to 0 into z to the power 0. Now this probability, we know that this probability is p. So the first term will be pz, and we know this probability is q. So the second term will be simply q, as it one is z to the power 0. Clear?
Yes, ma'am.
And we can check, if we evaluate this function at z is equal to 1, then we'll find p plus q, that is equal to 1. So now we are taking the first derivative. That means we are trying to find out the first moment. So we are taking the first derivative of this function. So that with respect to z, obviously. So, and that will give us the first moment, and look at this function. If we take the first derivative, the result will be simply p. So the expected value, the first moment that we have used, actually this moment generating functions are used for calculating the expected value and standard deviations for different density functions, for complicated density functions, right? That's why we are studying all these things in detail. So this is the expected value, right? And if we take the double derivative, this is the function. So the double derivative we know is equal to expected value of x square minus expected value of x, and that will come out to be is equal to 0. This is not minus. Z is equal to 1. At z is equal to 1. I'll check the Word file. So try to find out the standard deviation for this. Is this example clear?
Yes, ma'am.
Yes, ma'am.
Okay, next we'll consider another discrete distribution function, which is a binomial distribution function. Have you studied binomial distribution function?
Yes, ma'am.
So the binomial distribution function generally has two arguments. One is m, another is p, and it is described as Pn, that is probability x is equal to n, is given by mn p to the power n q m minus n for this range. So the first moment and the second moment, or rather, though it has been done over here. Okay, I'm not showing this. So you'll have to find out for this distribution function using probability generating function. You'll have to find out the expected value for this density function as well as the standard variance. That is your home assignment.
Okay, ma'am.
Okay. The variance will come to be equal to MPQ. Mean value you should calculate, and in the next class you should tell me the results. So
I will calculate.
it's a very simple problem. Now, moment generating function generalization. So any moment generating function can be written like this, that is expected value of this function e to the power vx. We have seen that at times we have taken v to the power v is equal to j omega, and in the second case we have assumed that the value of v is equal to s, isn't it?
Yes,
Yes, ma'am.
So we can generalize this moment generating function as expected value of e to the power vx, where v is the parameter. Right? Now, just I am showing you the Chernoff's bound since it's included in this particular chapter. But please remind me once I complete the uh, once I complete the next chapter, then please remind me. I'll go through this Chernov's bound once again. So a special case of this, as we have discussed, if we put v is equal to s, and as a result we obtain a Laplace transform, obviously with sign inverse. So we can generalize that. We can generalize the expression for moment generating function to be like this, and we obtain the moments, nth order moments, by taking derivatives, nth order derivatives of this moment generating function. Now, Chernov's inequality and bound is associated with this moment generating function. So the statement is like this. There are, what should I say, different statements in different ways. Chernov's bound can be explained. So we can explain Chernov's bound when we consider a moment generating function, as well as we can express Chernov's bound when we consider a number of random variables, a number of independent random variables, right? And please note down one particular term, IID, independent and identically varying random variable, that I'll explain when I'll discuss the density functions, or rather I'll discuss it. Please note the term IID. So rather when we'll discuss the fourth chapter, that means the bivariate or multivariate distributions, we'll consider number of more than one random variables. In that particular chapter, I'll discuss what is exactly meant by identically and independently varying random variables, or often we denote it as IID. So now one form of expression is like this, where we discuss Chernoff bounds in the context of moment generating function, right? So let x be any random variable, non-negative or not. So for any real value of v, please note down this expression mxv. Okay, so have you noted down the expression?
Yes, ma'am.
I've scrolled down. Anyway, so you see, this relation is always valid. That is e to the power vx minus a, this function, the area under this function, will always be greater than the area under this function. This is a unit step, and in this case we are getting some exponentially rising function, isn't it?
Yes, ma'am.
So I guess you'll agree that this relation will always hold.
Yes.
So here the statement is not written clearly. So I'll give you the statement. I'll incorporate the statement. Actually, what we are trying to prove, that probability x that x will be greater than equal to a. Remember Markov's inequality? So probability x that will be greater than equal to a will always be less than equal to this. That means e to the power minus va into mxv. What is mxv? Mxv is nothing but the probability generating function. That is the probability or moment generating function, to be more precise. This is the moment generating function. So if you want to find out this probability, that is probability x will be greater than equal to any arbitrary value a, is this probability is always less than this moment generating function divided by e to the power va. or this can be written in this particular form, that is probability x is greater than equal to a is less than equal to e to the power minus va into the moment generating function. Okay, so what is the proof? Let's go through it very fast. Probability x greater than equal to a will be equal to integration a to infinity fx dx, area under this curve.
Yes, ma'am.
So if I change the limits of the integration and if I consider the limits to be from minus infinity to infinity, then this area could be identified as fx into u x minus a dx. We define a unit state at that particular point, right? So from this we can write that this probability will be less than equal to, already we have seen this inequality, so we replace this by this. So fx, now we define the function as fx e to the power v x minus a dx, and we are taking integration from minus infinity to infinity. So now this part, the if I take e to the power minus va out of the integration sign, that I can do. So I'll get e to the power minus va, and within the integration sign we are having e to the power vx into fx dx. Do you get my point?
Yes, ma'am.
So that is nothing but, by definition, mxv.
Yes.
So this inequality, that is probability x will be greater than equal to a, will always be less than equal to this, is known as one form of Chernoff's bound. So do you have any question? Do you have any question?
No, no.
Then should I close the file? Can I close the file?
Yes, ma'am.